Welcome to Introduction to the Disk and Washer Method by Conceptual Calculus. This video is part of a series on applications of the integral. In this video, we learn how to use a definite integral to find the exact volume of a solid of revolution, which is formed by revolving the graph of a given function about the horizontal axis. We start with a simple object with a volume that is easy to find, the right circular cylinder. The volume of a cylinder is the area of the base multiplied by the length. For the cylinder in this example, the radius is 5, so the area of the circular base is pi r squared, which is pi times 5 squared, or 25 pi. The length of this cylinder is 6, so the volume is area of base times length, which is 25 pi times 6, or 150 pi. That's about 471 cubic units. Now, consider the region between this curve, y equals f of x equals 1/4 x squared minus x plus 2, and the x-axis, from x equals 0 to x equals 6. Revolve that region about the x-axis to form a solid. This is an example of a solid of revolution. We would like to find the volume of this solid. Whenever possible, we always start with an estimate. The simplest estimate for the volume of a solid of revolution comes from putting the object into a cylinder. You can think of the solid of revolution as a product we are preparing to ship. We put our product into a cylindrical package, such as a mailing tube or a can. This is explained in more detail in our video, The Can-It Method. The cylinder has a radius of 5 and a length of 6, which gives it a volume of 150 pi cubic units. The solid of revolution inside the cylinder must have a volume of less than 150 pi cubic units. There appears to be a lot of room for packing material around our product in its cylindrical package, so we can see that the volume of our product will be quite a bit less than 150 pi. After we find the exact volume, we will compare it to this estimate. The object is more complicated than a cylinder because the radius is not constant. The radius is shorter on the left and longer on the right. If only the radius were constant, then the volume would be very simple to find. The problem is more complicated because the radius is varying, is changing. That is an indication that integration could be helpful here. We break the object up into several parts and approximate each part with a short cylinder called a disk. This solves the problem of the varying radius. For each individual disk, the radius is constant. We take the radius of the disk from the curve. In this example, I'm getting the radius of each disk from the radius of the object on the right side of the disk. It is also possible to get the radius from the left side, or the center, or some other point in the interval. A couple of the disks are hidden inside the solid. We can see them better if we make that part of the solid translucent. You can see that the total volume of all the disks is close to the same as the volume of the object, but not quite the same. The disks leave out some volume that is in the object, and the disks include some volume that is not in the object. Now look at what happens if we make the disks thinner and use more of them. As the disks become thinner, they follow the curve more closely. In the limit, as the thickness of each disk approaches 0, so that the number of disks approaches infinity, the disks follow the curve perfectly. In the limit, as the thickness of a disk approaches 0, the sum of the volumes of all the disks is exactly equal to the volume of the object. To set up the integral, we start by understanding one disk very well. Then we can add them up. We need some way to keep track of which specific disk we are talking about. Instead of saying that we want the green one or the blue one, we use a variable as a unique identifier, sort of like the address of the disk. In this graph, the variable x gives the location of the right side of the thin disk. Because the variable x keeps track of which disk we're talking about, x is the variable of integration. Everything we do will have to be written in terms of x. In these problems, we always break a large thing up into small parts, and there is always some dimension that is very small, approaching 0 in the limit. In this case, that is the thickness of the disk. The thickness of the disk approaches 0 as we use a larger number of disks. As we move from the left side of a disk to the right side of the same disk, we go a little bit forward in the x direction. If we are talking about a finite number of disks, each with a finite thickness, then we call this width delta x. That little triangle is a Greek letter delta. When we consider the limit as the thickness approaches 0, then we call the thickness dx. Now that we have notation for the way the object is broken up into disks, we need to remind ourselves of what we're trying to find. We want the volume of the entire object, which we're going to find by adding up the volumes of the thin disks. So we need the volume of one disk. The disk is just a very short cylinder, so the volume of one disk is the area of the face multiplied by the tiny length or thickness of the disk. We have the thickness, it is dx. We need the area of the face. The face is a circle, so its area is pi r squared. This means we need the radius of the disk. Radius is distance away from center. In this problem, the center of each disk is on the x-axis, so the radius of the disk is the distance the disk extends away from the x-axis, that is, in the y direction. This means the radius is y. Since we are integrating with respect to x, we write everything in the problem in terms of x, so we need to write y in terms of x. We use the function for the curve y equals f of x, that is, 1/4 x squared minus x plus 2. Now we have all the parts we need to assemble our integral. The radius of a disk is f of x. The area is pi r squared, so pi times f of x squared. The volume of a disk is area multiplied by thickness, so pi times f of x squared multiplied by dx. To add the volumes of the disks together, we integrate. Our variable of integration is x, so the limits of integration must be values of x. The leftmost disk has x equals 0, and the rightmost disk has x equals 6, so we integrate from 0 to 6. Now that we have set up the integral, we can evaluate it. We have the integral of pi times f of x squared dx from x equals 0 to x equals 6. We put in the function f of x equals 1/4 x squared minus x plus 2 and multiply out the square. Then we use the power rule. The antiderivative of x to the 4th power is 1/5 x to the 5th power. The antiderivative of x cubed is 1/4 x to the 4th power. The antiderivative of x squared is 1/3 x cubed. The antiderivative of x is 1/2 x squared, and the antiderivative of 4 is 4x. Next, we substitute in the limits of integration. The upper limit is 6, so we substitute 6 in for x in the antiderivative. Then we subtract the same antiderivative with 0 substituted in for x, because 0 is the lower limit of integration. 0 to any of these powers is still 0, so this part is very simple. Finally, we simplify the arithmetic and find that the integral is equal to 31.2 pi, which is about 98. That means the volume of the solid of revolution is 31.2 pi cubic units. Compare this to the estimate. We determined that the volume was definitely less than 150 pi and appeared to be a lot less. A volume of 31.2 pi fits that description. When our calculation agrees with our estimate, we can have more confidence in our results. This was one of the simplest examples of using the method of disks and washers to find the volume of a solid of revolution. In later videos, we examine objects with holes in the middle and objects that must be broken into parts with a separate integral for each part. All of these problems will use the same basic method that was presented here. Conceptual Calculus thanks Dr. Harry Schuller, Chair of Engineering at Germanna Community College, for his gracious assistance with Autodesk Inventor, the software used to make the 3D images in this video. Thank you for watching Introduction to the Disk and Washer Method by Conceptual Calculus.